I am Laeticia Petit and I am a glass scientist. I investigate and understand the composition, structure, property relationships of optical glass-based materials with the main goal of developing new glass compositions with tailored properties to suit specific application needs related to photonics, such as optical communication, optical data storage, new lasers, and new photonic compounds and devices. Glass is one of the oldest and widest used material. The first man-made glasses were fabricated as early as 2600 BC in Mesopotamia. Glasses can be defined as amorphous materials, contrary to any crystalline material. The arrangement of the atoms possesses no periodicity, meaning that they do not exhibit any long-range order. Made entirely of raw materials found in nature, glass is simple and does no significant harm to the environment. Glass is both reusable and recyclable with endless lives. Glass can be recycled again and again in an endless loop. I have been interested in glass materials as they are used every day without even being noticed. Through the centuries, glass has kept on meeting people's and society's needs. For example, we use them for packaging, jars for food, bottles for drinks, flacons for cosmetic, tableware, drinking glasses, plates, cups, bowls, housing and buildings, windows, shelves, table, appliances and electronics, oven doors, cooktop, TV, computers, screens, smartphones, automotive and transport, windscreens, and more importantly, glasses have been engineered to carry information in phones, TV, computer, for example. Since glass has a wide variety of applications, glass must be prepared with different elements. With technology becoming advanced, there is a constant need for new glass materials with specific properties. So glass is not only a new trend or just a phase. 2022 has been declared the International Year of Glass by the United Nations to underline the technological, scientific, economic, environmental, historical, and artistic role of glass in our societies. Effort worldwide has been focused on laser, especially fiber. The concept of fiber laser relates to the doping of a glass with rare earth ions, such as erbium and ytterbium as the most common rare earth ions. Glass is a very suitable host material for optical applications because a large amount of rare earth ions can be incorporated in glasses. Glass provides a sufficient and stable environment for them. Laser glasses have been developed since 1961, when neodymium ions were first considered for laser applications. Since then, there has been an effort worldwide for the development of new luminescent rare earth doped systems, especially for applications which require high efficiency. We are interested in drawing these glasses into fiber, which is a flexible, transparent piece of glass with a diameter slightly thicker than that of a human hair. However, not all glasses can be drawn into fibers. The glasses needs to be thermally stable against crystallization, so the fiber remains amorphous during the drawing. In the photonic glasses group, we have developed the skills and facilities necessary to prepare high-quality lasing glasses. The group possesses furnaces dedicated for melting and sintering processes and post-processing. We have facilities for cutting, grinding, and polishing. Over the years, we have developed numerous glasses with various compositions, such as the borosilicate, telluride, phosphate, and germanate. For example, as part of our European Union's Horizon 2020 Research and Innovation Program, we developed new erbium phosphate glasses, the lasing properties of which depend on the glass composition because of the changes in the structure of the glasses. Our phosphate glasses have a polymer-like chains made of phosphate units. When adding aluminum or titanium, the network becomes more connected, associated with the formation of new bonds, leading to changes in the distance between the rare earth ions and so to changes in the lasing properties. These new glasses were found to be thermally stable, and thus we successfully drew them into fibers. These fibers were found to be bioactive, meaning they can be resorbed or they can link to new soft tissue once the therapeutic or sensing utility has been accomplished, so that the surgical removal of the fiber sensor is not needed. We demonstrated that it's possible to track the degradation and bioactivity reaction of an optically active and bioactive fiber after implantation in the body through the changes in the spectroscopic properties. Our investigations paved the way towards the use of optical fibers for the development of new photonic sensing probes, which could monitor in situ the dissolution and bioactivity behavior of the fiber inside the human body in the prospect of developing innovative biosensor for therapy monitoring. Another research activity is focused on the development of glass ceramics. Glass ceramics are glasses which are heat-treated in order to grow crystals. This glass ceramic can exhibit better performances than glasses if the rare earth ions are located in crystal with specific crystalline phase. To be promising for photonics application, the crystals should also grow in the volume of the glass, and their growth should also be controlled, so transparent glass ceramic with small-sized crystal can be prepared. Therefore, developing new promising glass ceramics is challenging, as not all glasses can be prepared into transparent glass ceramics. Nonetheless, we successfully developed transparent oxyfluoride glass ceramics with volume precipitation of erbium-doped calcium fluoride crystals. These glass ceramics are very promising as up converter. They convert the near-infrared into visible light, green light, for example. As it's not possible to control the nucleation and growth mechanism in glass, we have worked on the development of composite materials. These composites are composed of a glass matrix and crystal. So first, the crystal with specific phase and dopant levels are prepared, then added in the glass melt before quenching. In this process, it's crucial to identify a suitable temperature for doping and dispersing the crystal in the glass melt to succeed in doping the glasses homogeneously with particles. The particles need to be, of course, thermally stable at this doping temperature to ensure the survival of the particles within the glass during the glass preparation. Using this technique, we prepared new glass-based composites with persistent luminescence, for example. Persistent luminescence refers to the type of emission which lasts for a long time after the removal of the irradiation source. The persistent luminescence was obtained by adding persistent luminescent crystal in the glass. These composites could find application in bioimaging, for example. Indeed, one important problem is the imaging post-operation of bioactive glass-based implants, as they often appear radiotransparent in X-ray imaging. The tracking of the implant's reaction in vivo and in real time is important to solve, as despite their fast degradation rate, glass particulates are still surprisingly present in the body after 14 years post-operation. In order to determine the amount of new mature bond formed, in vivo testing are performed and animals are sacrificed. Therefore, there is a need for implants which act also as a new in vivo imaging device. By irradiating the patient with a safe light which penetrates the skin, the in vivo imaging device will allow one to monitor in situ and over time the implant resorption without the use of X-ray. With our collaborator at the University of Turku, we are currently working on the technology based on nanoprobes with near-infrared persistent luminescence, as it corresponds to the wavelength in the tissue transparency window. Using similar technology, we have been working on near-infrared rechargeable composites with green persistent luminescence. So this was achieved from an ytterbium-thulium photoglass, which exhibits green persistent luminescence after being charged with the near-infrared light. The combination of ytterbium and thulium results in the possibility of an absorption of near-infrared photons, like the ytterbium, followed by an energy transfer to the ytterbium, which later completes the upconversion process by emitting blue light. It is this blue emission which charges the persistent luminescent particle, leading to long-lasting green light. This near-infrared conversion to long-lasting visible light could be useful for various applications, in solar cells, for example, and also in biomedical applications. Indeed, as an internal stimulus, light is a powerful tool for triggering chemical reaction in biological environment with rapidity and accuracy without affecting important physiological parameters, such as the temperature, pH, and ionic strength. Although light has been used to locally activate photosuitable drugs, most of these drugs usually absorb ultraviolet or visible light, which does not penetrate the skin. Thus, the near-infrared conversion to long-lasting visible light allows the in situ delivery of drugs. These are just few examples of the glass-based material development from the Photonic Glasses group at Tampere University. As said already, the exploration of new photonic glass-based materials is the key for advanced photonics devices. There is no doubt when I say that we live in the new age of glass, and I hope that we at Tampere University will play an important role.